Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button. Subscribe to our channel. Share it with your friends who are preparing for their competition and boards as well. Alright. Do not forget to click on the bell icon so that you never miss any update from us. Okay. Now let's start with the session. So we were doing electrostatic potential and capacitance, and this is lecture number 2, where we'll be seeing electric potential due to electric dipole. Right? Electric dipole, we have already studied about electric dipole in the last chapter, right? Then we studied about dipole moment. We studied about electric field due to an electric dipole, right? I hope you all have done the revision and you know what is it. All right. In this session, we'll be seeing electric potential due to an electric dipole. This session will be very small. Only electric potential due to dipole we'll be discussing, where we'll be seeing the end-on position, the broad-on position. That means electric potential at a point at the axis, and then electric potential at a point in the perpendicular bisector of the electric dipole. Then electric potential at any point due to electric dipole. Alright, only these three things we are going to see. I hope you are ready. Take out your notebooks and pens. We'll do the derivation. Again, it's very easy. You can do on your own also. Now, on the axis of dipole. So this is a dipole, negative charge, positive charge, equal and opposite charge, right? Minus q plus q. And this distance from the center we take usually. So this is L from center to this charge, and from center to this charge, this is also L. We have to find electric potential at a point on the axis. So let's take, there is one point P on the axis. Okay. We have to find electric potential there. This point P, let's say it is at a distance of x from the center. Now, again, very easy. At this particular point, we can write electric potential due to this charge. At this particular point, we can write electric potential due to this charge also. And then it is a scalar quantity, we'll add up, right? So V, all right. V at point P is equal to V due to minus Q plus V due to plus Q, right? So this will be K into Q divided by the distance between this charge and P from minus Q. So this will be, this is x, from here till here this is x, this is extra L. So this will be x plus L. Then here plus V of plus Q. From here, electric potential at this point due to this charge, it will be K into Q divided by this distance is x and this is L less than x, right? So this will be x minus L. So now here, one more thing. This will not be kq upon x plus L. This will be minus kq upon x plus L because it is a negative charge. So the potential will be negative, right? We discussed this in the last session. So now this will be Vp is equal to kq upon, I'm writing this side and this one this side, okay? So that it becomes easy for doing the calculation. Kq divided by x plus L, correct? So now kq will be common. This will be 1 upon x minus L minus 1 upon x plus L. So here kq, x plus L will come here minus x minus L divided by x square minus L square. Yes or no? X minus L into x plus L. X square minus L square. That is equal to, now here if you see, this x and this x will be cancelled. This is plus x, this is minus x. and this is plus L minus minus plus L. 2L will be coming at the numerator, right? So this will be K Q 2L divided by x square minus L square, right? Now, can you see the dipole moment here? Q into 2L. What is this? Here, the distance between the two charges is 2L. So the dipole moment will be Q into 2L. So here, this Q into x is very, very greater than this L, right? Why? Because this distance is very small. It will be in micrometers and this x will be in millimeter or centimeter, right? So this will be x is very, very greater than L. So x square minus L square, I can write it at, sorry, this is nearly equal to x square, correct? So this will be Vp is equal to Kp upon x square, or we can say V at point P is equal to 1 upon 4 pi epsilon naught P upon x square, right? Remember this one. Both are same only anyways. That I have just substituted K as 1 upon 4 pi epsilon naught. Clear? Epsilon naught because we are seeing in air or free space or vacuum. Okay? Kp by x square. Now, here what you have to see is this V is inversely proportional to x square. Now, if you remember electric field due to electric dipole, 2 Kp by x cube, right? 2 Kp by x cube. Always compare whenever you are seeing any new quantity, always compare with the older one, whatever you have studied. This will help you to retain the things. Okay. So this is Kp by x square. Now here, forget about this thing, right? Okay, this is the same thing we are talking about. V is inversely proportional to x square, right? So if you want to write the graph, make the graph also. Let's say this is R, or I'll write x only. This is V. Inversely proportional x square, it will be like this. Draw it. Clear? Here if the charge is there or the dipole is there, it will be like this. Alright. Now, on the equatorial plane of dipole, so this is a dipole, equatorial plane, last time also I explained. What is equatorial plane? A plane which is equidistant from both the charges. So where will that plane be actually? That plane be on the perpendicular bisector of these two, of this dipole, right? The perpendicular bisector means this. A plane passing through this perpendicular bisector will be the equatorial plane. Yes or no? So here I can actually write on the equatorial plane, or I can write perpendicular bisector also. Correct? I can write perpendicular bisector also. Any point which will be on that equatorial plane will be on the perpendicular bisector also. Understand? If there is a plane like this, now it is coming out also and it is behind this line also. Alright? Any point here, from this charge it will be at some distance, and from this charge it will be at some distance, and both the distances will be same because this plane is passing from the mid. Correct? If this point is here, from here to here, from here to here, the distance will be same. And if you only see this two and this line, if I join this center and this plane, this point, if I join this center and this point, this line will be perpendicular bisector. Yes or no? That means equatorial plane of dipole or perpendicular bisector, we can say it as the same thing. Alright? Now, this charge is minus q. This charge is plus Q, L, all the same thing. This is point P, which is at the perpendicular bisector, or we can say the equatorial plane. Now here, I have to find potential. This point is at distance x. Okay. This point is at distance x. How to write the potential? Again, since it is potential, nothing to worry about the direction and all. It is a scalar quantity. We can directly write theorem. Yes or no? From here to here also, this distance under root x square plus L square. Correct. So this will be minus kq under root x square plus L square plus kq divided by this distance, that is under root of x square plus L square. Now can you see one thing? These both will be cancelled. These both will be cancelled. Finally what we got is 0. That means potential at any point on the equatorial plane of the dipole will be 0. Any point. Alright. So if this is the plane, let's say, any point in this plane, here, the distance from this charge and this charge both are same, because this plane is passing from the mid. Any point here, the distance this and this both are same, because this plane is passing from the perpendicular bisector. Clear? Passing from the mid. Alright. So in this entire plane, how much ever this plane is, or let's say this plane is very big, it is infinite, how much ever this plane is, on this entire plane the potential will be 0 due to the dipole. Alright. Okay. I hope you got it. Now this kind of plane, where any plane where at each and every point the potential is same, is known as equipotential surface. It needs not to be only 0, it can be any value, but if it is same on all the points of the plane, that is known as equipotential surface. That we'll study in the upcoming sessions. Alright. In the next session mostly we'll study. Understood? Note it down. If you want, you can write down equipotential surface. First of all, V at P, or let's say you can write V at perpendicular bisector. Or V perpendicular only you can write, is equal to 0. Here this is V axis. Alright. V perpendicular is equal to 0. If you want, you can write down, since at all the points on this plane the potential is 0, it is an equipotential surface. Then, do you remember the electric field at the perpendicular bisector or the equatorial plane? Kp by r cube, right? On the axis it was 2 kp by r cube, and on the perpendicular bisector it was kp by r cube, and here it is 0. Okay. Next. Now, at any point, so now let's say this is a dipole, minus q plus q, L. Let's say there is any point P which is at a distance of r and at an angle theta. Any point will be, the coordinates are r comma theta. Okay. R comma theta means it will cover everything. Everything it will cover. Any point, if you see r distance, let's say r is 10 centimeter and theta is 45 degrees. It will come somewhere like this, right? Let's say r is 20 centimeter. This is some random point P whose coordinates are r comma theta. That means the length is r centimeter, the length is r units, and angle is theta. Alright. We have to find potential at this particular point. What do we do? Now here if you see, again, the people who have attended the last chapter where I was talking about electric field due to the dipole, they will easily able to do it, right? But here, the people who are seeing for the first time, what they'll think is, oh, from here, this distance is different. From here, this distance is different. Now, first we calculate the distance from here. Then we calculate the distance from here. Then we find out the answer, what this theta will be. According to this theta, the way to take out this distance will be different, right? If theta is 90, you can directly take out by Pythagoras theorem. But if theta is different, you have to put different mathematical formula to find these two lengths. Correct? So now, instead of making it very complicated, we can find it easily. See. Now, let me make you understand. This is an electric dipole. P. Okay. Now, this dipole, what we'll do, we'll take two components of this dipole. We'll divide the dipole into two components. Okay. One will be along this theta. So this component will be, if we'll take along the theta, this component will be P cos theta, correct? Perpendicular to this P cos theta will be P sin theta. Yes or no? Let's say from the horizontal, this is P, this is theta. So this will be P cos theta and this will be P sin theta. Now P sin theta is perpendicular to P cos theta, right? This is horizontal component, this is perpendicular component. The same way, along theta, we'll get horizontal component and the perpendicular component will be P sin theta, correct? Now, after taking out the components, forget about this P. This P, I'll make it with a different color. This P. Forget about this P. Now we are not finding the potential at this point due to this dipole. We will be finding potential at this point due to two dipoles. That is P cos theta and P sin theta. And see how easy it will become. At this point, we will not find out potential due to this P. We will find out potential due to P cos theta and due to P sin theta. And then we'll add it. Alright? The answer will be same. Why? Because this P cos theta and P sin theta are the components of P only. So whatever potential you will get due to this P, the same potential you will get due to P cos theta plus P sin theta. Alright? So V at P will be equal to V due to P cos theta plus V due to P sin theta. Now understand why we took two components, so that the question becomes easy. How will it become easy? For this particular dipole, if you see, this point is at the axis of the dipole. For this dipole, this point is at the axis of the dipole, and we know the formula to find the potential at the axis of the dipole. For this dipole, if you see, the same point is at the perpendicular bisector of the dipole. This is at the center, right? So this, if you see this point P, this line is perpendicular, correct? P cos theta was perpendicular to P sin theta. This is in the same line. So this point P is at the perpendicular bisector of P sin theta. We know the formula for perpendicular bisector also, right? That's why we did two components, so that the question becomes easy for us. So now V due to P cos theta, since this point is at the axis, we can write Kp by the distance from the center R square, correct? But here this P will not be P. There we took out at the axis due to dipole P. Here the dipole is not P, it is P cos theta. P cos theta. Clear? K P cos theta by R square. I hope you remember. At the axis, see, at the axis, Kp by x square, right? Now this Why P was there? Because due to this dipole, P, we found out. This was the dipole at the axis we found out, right? Here, this time, the dipole is P cos theta. At the axis of P cos theta, this point is there. So it is Kp cos theta by r square. And V due to P sin theta. Now this is at the perpendicular bisector, so the potential will be 0. At the perpendicular bisector of any dipole, potential is 0. So here this potential is 0. So finally what we got, V at P is equal to Kp cos theta by r square. This is V at any point P. Clear? This is V at any point P. If you want to check, you can put theta as 90 degrees. What you will get? 0. And we know due to this particular dipole at perpendicular bisector, V is 0. Put theta as 0 degrees. You will get on the axis. 0 degrees means it is on the axis, right? So this will be Kp by r square. Correct? The same answers you will get. So this is a general formula. General formula. For boards, only at the axis and perpendicular they will ask. This is for competition, some extra thing. All right? Note it down. Got it? So now understand one more thing. In questions, sometimes they will not ask on the axis. They will say end-on position. Sometimes they will not say perpendicular bisector or equatorial plane. They will say broad-on position. So this position, the first one, this you can also say end-on position. Clear? And this you can also say broad-on position. So don't get confused if in the question they will mention like this. All right? Okay. This was today's session. That's all. Now let's see some 2 questions. The distance between H plus and Cl minus ions in the HCl molecule is 1.28 angstrom. So this is a question with data. The same thing which we have done, we have to apply here. Okay. H plus and Cl minus. H plus is here. Cl minus is here. The distance between this H plus and Cl minus is 1.28 angstrom. Actually, it is not this much. Angstrom means 10 power minus 10 meters. Correct? So this will be very small. What will be the potential due to dipole at a distance of 12 angstrom on the axis of dipole? 12 angstrom means on the axis of dipole they are asking. From here, now this distance is very small. We can take this from the center, 12 angstrom. From the dipole, if it is written, means from the center it is given 12 angstrom. Clear? Now how do we do this? This is some point P. This is the dipole. This is point P. We are given with this distance, this. Can you find out? It is easy. You just have to make the diagram. That's all. Once you make it, question becomes easy. Now here, one more thing. How much charge you will take? See, we know that V at P, since it is at the axis, it will be K P by R square. Correct? Or X square, anything. P is not this P. This is point P. What is the value of this? Nothing. P is Q into 2L or Q into L. Q into the distance between these two. Dipole moment. Do not remember as Q into 2L. Otherwise, you will multiply this by 2. I already told you this confusion. Q into the distance between the charges. Correct? So this will be K is 9 into 10 power 9. P is Q into Q into this distance 1.28 into 10 power minus 10. divide by this distance 12 angstrom square r square, 12 into 10 power minus 10 whole square. You can do that also. If you remember x square minus l square, we assume that x is very greater than l, because of which x square minus l square we wrote as x square, or r square minus l square we wrote as r square, correct? You can actually do this also, 12 into 10 power minus 10 whole square minus this distance, half of 1.28 is 6.4, correct? 0.64. 0.64 into 10 power minus 10 whole square. The answer will be nearly same from both, from this also, and if you subtract in the denominator with 0.64 into 10 power minus 10 square also. Alright. Now, what will come in the place of Q? What will come in place of Q? Here H plus and Cl minus. It is because of one electron is more, here one electron is less. Correct? The charge of one electron, 1.6 into 10 power minus 19 will come. Clear? This Q will be 1.6 into 10 power minus 19. Now I hope you will be able to solve it. 9 into 10 power 9 into 1.6 into 10 power minus 19 into 1.8 into 10 power minus 10. Now this is dipole moment, charge into the distance between the charges, and this is this distance square. Yeah. If you solve this, you will get one answer, that is 0.13 volt. It will be around 0.129. So you can write it as 0.13 volt. Clear? Note it down. Or write the question, try doing it on your own. Remember the answer. Okay? Next. Figure shown below. The figure below shows the field lines of a positive and negative point charge respectively. This is a positive charge, this is a negative charge. Field lines, how will it be? This will be outwards. This is a negative charge, this will be inwards. Correct? So now, first question is, give the signs of the potential difference Vp minus Vq and Vb minus Va. Vp minus Vq. Give the signs means whether it will be positive or negative. Think PQ here. That means potential at P minus potential at Q. Will it be negative or positive? Again, since we have studied potential, it is very common sense, very easy to understand. Positive charge. The more near we are to the positive charge, the potential is more. If you remember the last lecture where I told the more near you are, the influence of the charge is more. The far you go, the influence of the charge decreases, right? The more near you are to the charge, the potential is more. The far you are away from the charge, the potential is less. So here, Vp will be greater than Vq. This we can write. Vp will be greater than Vq. Arey bhai, V is inversely proportional to R. V is equal to KQ by R. So that means the more is the distance, the less is the potential. The less is the distance, the more is the potential. Here the distance is less than this distance. Correct? So Vp is greater than Vq. Alright. Here, no doubt V is inversely proportional to R, but a negative sign comes with negative charge, right? The more near we are, the magnitude will be more, no doubt, of the potential, but it will be with a negative sign. So here, this will be negative bigger quantity, this will be negative smaller quantity. Correct? So basically, Vb will be greater than Va. I hope you get it. If suppose this is minus 2, this is minus 4. Magnitude will be more, no doubt, but a minus sign will be there. Magnitude will be less, but a minus sign will be there. Which is greater? Minus 2 is greater. Vb is greater than Va. Clear? Alright. So now Vp minus Vq. Vp is greater than Vq. This will be positive. And VB minus VA. VB minus VA. Again, this will also be positive. Why? Because VB is greater than VA. Clear? Next. Give the sign of the work done by the field in moving a positive charge from Q to P. Again, you have to go back to the first lecture. Give the sign of the work done by the field in moving a positive charge from Q to P. Now, what you have to notice here is work done by the field in moving from Q to P. Here, and you have to see which charge you are moving. Correct? Positive charge. P to Q. Okay, Q to P. Q to P. Here they are telling from Q there is a positive charge kept. You are moving this positive charge from Q to P. You are not moving. Field is moving. Give the sign of the work done by the field. Now here if you see, if a positive charge is kept here, what will the field do? The field is outwards. This is a positive charge. Positive charge will repel the positive charge, correct? Positive charge will repel the positive charge. That means this positive charge will make this charge go away. But what they are asking is, what is the work done by the field in moving small positive charge from Q to P? It will not come from Q to P, right? This charge is kept at rest. Correct? It will not come from Q to P. So from Q to P, if we have to take this charge from Q to P, the work will be done by the external agent. And work done by external agent, work done by field is negative of work done by external agent, because this is opposite work done. Correct? Field will make this charge go away, but they are asking if the field will make this charge go in this direction, that will be a negative work done. Correct? So this will be, why it is a negative work done? Work done by field will be negative. Work will be done by external agent. Therefore, work done by field will be 0 in this particular case. All right. Clear? Common sense? Next, give the sign of the work done by external agency in moving a small negative charge from B to A. Small negative charge from B to A. So what all things you have to see? Work done by external agent they are talking about. Here they were talking about the field. Here work done by external agent, then a small negative charge from B to A. Clear? See here. Negative charge is kept here. From B to A. This is negative. This is negative. Negative will repel each other. That means this negative will make this negative go away. Alright. If it is going away, the work done will be positive. But what they are telling is, now this charge has to go from B to A. This charge has to go from B to A. Now B to A, this work will be done by external agent, because naturally this negative charge will push this away. So there should be an external agent who has to do work against the field to make it go till A, right? That means work is done by external agent from B to A, and they are asking work done by external agent only. So it will be positive. Since work is done by external agent only, has to be done by external agent in moving the charge from B to A. It will be positive. Clear? Here, since they are asking by external agent, the work done has to be done by external agent because it has to go opposite to the field. So it will be positive. If they would have asked by the field, it will be negative. Clear? This is not 0 what I have written. Work done by the field will be negative. Sorry. Okay. work will be done by external agent, therefore work done by field will be negative. Clear? Next. Does the kinetic energy of a small negative charge increase or decrease in going from B to A? Again, common sense. These kind of questions are very good, cute questions, cutie pie questions, right? Does the kinetic energy of a small negative charge increase or decrease in going from B to A? Now let's say, first they are asking about the kinetic energy of a small negative charge. Alright, going from B to A. B to A. Now again, if you remember this particular thing only, negative charge is there. From B to A, this negative will repel this negative. Correct? This will send it away. That means the force on this negative is in this direction. Force on this negative is in this direction. Now suppose this negative charge is going from B to A with a very high velocity. Suppose I have sent it from B to A with a high velocity, or some external agent has sent it from B to A with a high velocity. The force is continuously in the opposite direction. It will continuously repel. Force is mass into acceleration. The acceleration is opposite to the velocity. If the velocity is in this direction, the acceleration is in this direction because the force is continuously repelling. Correct? So acceleration is opposite to velocity. What will happen to velocity? Velocity will decrease. Here, velocity, since force is in opposite direction to the moment, electrostatic force is in the opposite direction of the moment velocity of the charge will decrease. And if the velocity of the charge will decrease, the kinetic energy will decrease. Hence, kinetic energy decreases. Clear? Simple. This question was from your NCERT. One more question was there regarding the potential energy. When we'll talk about potential energy in the next session, then I'll give you the question, that particular question. All right? Done? So I hope you liked today's session. It was very easy, right? In the next session, we'll be talking about equipotential surfaces and relation between field and potential. Okay? So this session was a small session. We completed it fast. Just make sure you practice potential due to dipole on your own. All right? If you like today's session, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. We'll meet up in the next session. Till then, keep learning from We Learning. All the best.